and I'll go. Hey, Magda, how are you doing? I'm going to
Good.
drop the.
Again,
You do.
lovely to see you back, Ed.
Thank you so much. I'll take it. Thank you. I was hoping that I would see you today and Jimmick. So I have a Polish data set that I'm going to use as a demonstrator. I can't remember if there's anything that I needed your input on, but if there is, I'll be sure to yell out.
Yeah, please feel free.
Let's see. Okay, now I think I have highlighted myself to everybody, so I should, my screen should be big and I hope everybody can see. So I'm going to go ahead and start talking today because I want to be able to get through it. What I'm talking about today is synthetic data. And I'll explain what that is and how it applies to agriculture. And I've given this a subtitle, a positive subtitle of why farmers should care about fake data. But this really was inspired. I got really thinking about this. It's been about a year, and I was interacting with a colleague at a different institution who does something very different to what I do, but who at that time was leading a group that did more or less agriculture engineering kind of stuff. And so I thought we were right on the same page for some of the stuff we were talking about. And I mentioned the idea of synthetic data, which I will explain during today's session and demonstrate um, um, to you. But the reaction that I got from this fellow was that farmers don't care about fake data. They're not interested in that. And so there was such a profound. I was surprised that this person had not even heard of the technology that has become important in statistics methodology these days, and especially with AI, that's called synthetic data. And it's a way of one of the primary uses is to anonymize data that has intellectual property or sensitivity, such as medical records, but also could apply to farm data, as I'll argue today. Anyway, that's what's inspired today. Next week, we're talking about, I'm just looking across the people that are here today, and I don't see Sophie in the room, but I think I'm going to give an example statistical consulting session on effect size, power, and calculating the required sample size to achieve a particular power for a particular problem next week. That's a perennial favorite. And then have some slots. If there are any volunteers, feel free to pip up, or else I'll populate this with things before Christmas. Okay, so without further ado, I'm going to launch in. I have a few slides, but I wanted, in part, to address what I perceive as maybe some confusion about what synthetic data are, but probably to introduce it for the first time to people who aren't technical or data people. So I hope this is good for everyone. So in general, there's a need for capturing agriculture data these days. And we are a research institute in agriculture, but this is permeated down to farmers who are open to such things. And they want to make data-informed decisions to primarily increase efficiency, to increase competitiveness in what they do. And this is due to a lot of reasons. Input costs are rising. There's constantly the warning and pressures to increase your environmental sensitivity on farm, and regulations to mandate that. Labor shortages are pushing automation and being more precise to shave a few percent off of efficiency concerns. Climate change creates an environment that's unpredictable, especially here in Britain with extreme weather events, flooding and droughts. Well, the solution to that is that if we collect a lot of data about what's going on in the farm, we have the posit that we can reveal hidden inefficiencies and then to in some way optimize farming activities. Now, agricultural economists have been doing this for ages, And because of recent technological advances with GPS systems and data systems and GPS and work cycle loggers on almost all new farming equipment that's sold by every company, um, there's this idea that all of this data is going to be very valuable to farmer. And there's this phrase, data driven farming. I think it's still a hopeful phrase at this time, but that's the aspiration that we're going to use this data and it's going to be a lot better in the future for everybody. Well, um, I've mentioned this before, possibly even here in Herrig, but there's a problem that I call the GEM conundrum, GEM, and this is the genotype by environment by management problem in agriculture. And this is specific to data. When I'm thinking about data, collecting data on farms, one of the challenges, in my view, is what I refer to as the GEM conundrum. And the GEM conundrum is the fact that even on a single farm, the constantly changing genotypes of plants and animals creates unpredictability. Environmental fluctuation and changes in the greater trend of environmental patterns creates unpredictability. And management changes, sometimes correlated to genotype or correlated to environment, but sometimes due to opportunism or changing availability or just practical concerns, is constantly changing. Now, if these things changed in a systematic way, that would be a problem, but they don't. They change in a haphazard or a random way, and they do so both within farms and between farms. So this creates a challenge to be able to make sense for generalities for a specific farm. Now, the solution to this, a solution, is really to create massive multiple farm long-term data sets. And this is kind of the dream for, I don't know, Michael Lee, I think, has a dream that, that this can happen if we just start doing it. Um, I've only seen a few medium-sized agriculture data sets that even begin to broach this. And there are a couple of reasons why this problem with an easy solution, just to collect lots of data from lots of different farms, has just not happened, and it's not about to happen anytime soon. One reason is that data collection and especially data sharing is certainly not a tradition in agriculture. Farmers have a distrust of companies. It's probably well founded, as far as I can tell, and they're reluctant to share sensitive data for all sorts of reasons. They don't want to release market information to competitors. They don't want to release productivity data necessarily to buyers. They don't want other farmers seeing what they've gotten up to. And sometimes they may have things that they want to, keep private about their business. So there's in general just a lack of a standard system. Now, when companies, let's take John Deere for example, when they sell a tractor, you you probably are going to have some data, automatic data collection out of the box, and you can pay a little bit depending on what kind of implement or machine you have, and you can collect a lot more. And I believe that you get some of your own data back through. I can't remember the name of the John Deere data tool. If somebody does know what that's called and remembers, put it in the chat, please. But I believe you get some of your data back for free, but they want you to pay. They want farmer to pay for data that they collect on implements that you own. My John Deere is indeed what it's called. Thank you, Megan. Um, this is just one system, but really one of the points I want to make is that for a solution to the GEM conundrum for data science engineers and other entrepreneurial engineers across the industry, we really need shared long-term data for many, many farms. and it's it's the the systems that we have, both the social systems for farmers and their distrust of data sharing and companies, but also the structural systems, by which I mean the enterprises that gather data. At the moment, they are mining data from farmers as if it's gold ore from the ground, and they're keeping all the gold to themselves. Um, Now, a lot of people might view this as just the normal course of capitalistic activities. But if we actually want to create information, we're going to have a sensibility check here, sensibility check in a big way. That data for a single farm, a farmer getting his own data back has almost no value. The value that farmer might get from their own data would be massively amplified if there was a context, a wider context showing benchmark-like values, metrics, compared to the operation of other similar farms based on many, many measures. And it's collection of this long-term data from many farms that will be able to chip away at the Jim conundrum and build models. Um, it's hard for me to see, I don't want to be negative about this, it's hard for me to see a single solution to this. But what I'm going to talk to you about for the rest of the talk and demonstrate in the code is a potential solution for some of these issues, and that's synthetic data. Now, a thing about synthetic data is that I'm just going to say this verbally, um, that it is a tool set that is meant to preserve statistical properties of all kinds of data sets. That's used for artificial intelligence training data sets more and more, but also tabular data sets and databases for different industries. And I'm arguing here that it's barely been used at all in agriculture. Maybe one of the reasons because big data sets just simply don't exist exactly like I'm talking about for the reasons I've talked about. But in general, this technology has been applied to other industries for these reasons, that it preserves privacy by anonymizing individual records in data sets while preserving the all of the statistical characteristics of data sets. If you remove privacy concerns and intellectual property concerns, this immediately loosens the reticence to share data. There's no reason not to share it if it's just a set of statistical weights. And in medicine, for example, where synthetic data is just having an astronomical amount of success in advancing modeling, and especially the development of AI models, but even traditional modeling of disease incidents, it massively improves the access to this information. Whereas as before synthetic data, to have access to the actual patient records, there are massive amounts of bureaucracy, red tape. It's also very expensive because many companies want to sell it, including an allegation that the NHS wants to sell it to Trump's American companies, I suppose. Anyway, if we have this anonymous data, again, back to the positive things, one could say it encourages collaboration by literally by reducing any concerns over leaking sensitive information. And I mentioned it's been used in healthcare quite a lot. If you just are interested in this, you'll see a lot of highly cited papers talking about applications and the assemblage of different data sets. In fact, even just this morning, I my ear is tuned to cancer news and cancer advancements, and they're talking about using AI for predictions. And this kind of approach has really revolutionized that kind of diagnostic tool and diagnostic devices the world round, also reducing the cost of them. But other industries as well, finance and social sciences and we said if you look, you don't have to look very hard, and you just find thousands of papers that have been published in the last 5 years or so, especially, and lots of reviews already about it as well. And ultimately, what this method does, there are different kinds of approaches to synthesizing data, but all of them have some similarities. For example, um, almost all of them start with a fairly robust data set to start with that has usually we're talking very large data sets. This is big data kind of stuff that you might get from social media or a national health database or international finance records. We're talking for an ideal application, very large data sets. But essentially, what every one of these processes has in common, even though there are many methods and many fields it's applied to, is it starts with a data set of some description and it exploits uh, probability distributions of the occurrence of particular data. So, for example, on the left here is some data for the hours spent sitting, in a single go, and it represents a particular statistical distribution that can be described, and if it can be described, it can be modeled. Now, this is a gross simplification of the actual problem, because one of the things I want to communicate to you, even though I'll show you a tidy script that that operates on a 5,000 row data set, and I think I have it set up to create a 10,000 row synthetic data set, which I'll demonstrate to you. This picture that I've shown you is just one variable, but to actually create synthetic data, oftentimes you have data sets that have many, many variables, and the probability distributions that we're talking about are joint probability distributions between many variables. Now, I don't want to go down the rabbit hole of all the intricacies and complexities, but I wanted up front to state that it's actually a fairly sophisticated problem that requires a fairly sophisticated solution. So what do we do with it is, well, I've been thinking about these things for a while now because there are several data sets that I have been working with that I would like to create synthetic data from, specifically for academic reasons and to share on for modeling. One of them is the PRISM data set. I see Carl in the chat. I would love to use the PRISM data set to do this for carbon emissions on farms. It's a relatively small data set for a full synthetic data exercise, but it's been a while since I've looked at it, but I recall it's about 300 farms-ish, and I think we should have 2 or 3 years of the data by now. And so it's a candidate that I would like to explore. Another one, and I see Eric in the chat, is an exercise with a multi-farm longitudinal data set for chicken ammonia emissions and productivity that we are collaborating with some chicken farmers for. I guess they wouldn't prefer to be called chicken farmers. Let's call them poultry farmers out of respect. I would love to turn that into a synthetic data set, and I think they're open to that. So this is something that's touching my current research interests that I plan to pursue. So this would allow us to collaborate with people, maybe people that other academics that aren't directly involved with the project. It's always an issue. Can't remember if we signed a non-disclosure agreement with the poultry people, but I think for PRISM we are under some data restrictions. So this would allow research collaborations that are otherwise unavailable. It'll allow us to quickly develop and test models. Now we can do that anyway with a data set if you have access to it, but the thing with synthetic data is if you start with 5,000 lines it's easy to make 10,000 or 50,000 lines of data in simulation. And likewise, we can enhance the data sets by balancing them. This is a big deal. This is one of the big advancements in synthetic data for medical diagnostics, where there's a big literature. So I've kept my finger in medical biostatistics over the years and started my career doing work in that field. And in diagnostics, synthetic data has solved this huge ethical problem that many of the available data sets are essentially white, male, middle class American people. That there are these long-term data sets that are merely available, and data from other socioeconomic groups, data from other countries, and especially data from minorities, and even data for women are often lacking in these data sets. And it makes the predictions that arise from data sets based on biased source data invalid, wrong, in some cases, very wrong. So this is a big advantage, and it's one of the primary areas of research, especially in application to the medical industry. And of course, we can use this stuff for education and outreach, and even if there are compliance concerns and data privacy concerns, it's an easy way. For example, if people really don't want to share their data, this is again something that's driven by the medical industry. The raw data in some form have to be released to the analysts, except if you have synthetic data, in which case it doesn't at all. And so it immediately solves a compliance problem. All right, so code time. Now, I think one of the things I wanted to show you is that if you like following along and like doing this kind of stuff, I've put a link to the GitHub, and if you open it, you'll just see this. If you just you don't even need the project file, you just need the R script, and you can just open it and copy it if you wanted to. I'm going to open it locally on my computer. RStudio as usual. Now I'm going to get rid of everything. It looks like we're clean to start with. I'm going to make it a little bit bigger for people. And I'm going to go up to the top. And so for this, I'm going to be using this library called the synthpop library. There are other options that are out there, but the synthpop one balances simplicity with power, as far as I can tell. I really like the synthpop package. It's not a traditional R package, which in some ways is a good thing because traditional R packages are all over the shop. So I like the focused nature of synthpop. So it is my favorite synthetic data set tool, and I've done some quite a lot of data simulation over the years, mostly writing the code and functions myself when I need to. And one of the applications that I've had a lot of experience in is in experimental design, where you are planning an experiment, you have an idea of an effect size, and the model is more complicated, maybe has multiple factors, and then exploiting the joint distribution of those factors in a linear model is something you can simulate. So that's my main foray into data simulation before the last year or so. Synthpop is bang up to date. As you'll see, it uses classification and regression, random forest, or random forest-like methods, which we've talked about here a lot, which are called CART methods, C-A-R-T, or classification and regression trees. Okay, so we're just going to load up the synthpop library. It should load up. I've included the code in case you need to install it. Now, in the data set is some data. In the library, rather, are some supplied data sets. I like some of the things about this. It's even funny in this library. They've called the supplied data sets SDs, supplied data sets. And this is a data set. Now, this is a survey data set from Poland. And we can just look for a little information about it. We can kind of look at some of the variables. This is 5,000 observations from what they called a social diagnosis survey from 2011, so quality of life. And there are, gender and age group, place size. I'm not sure if this is the size of the town or something like that. The region, the voivodeship. Now, I think the voivodeship is something just like a shire or a county here in England, and I think a voivode is something like a duke or something like that. But the the Polish people in the audience can correct me. Okay, I was hoping that was correct. I find history in the eastern parts of Europe so fascinating, but I know too little about it. Okay, so it goes on. Um, yeah, and this is just an administrative section of the country. We're not going to do much with it, I have to say, but let's look and see how much data we have. So I've done the dim function to determine that we have 5,000 rows and 35 variables. Now, this probably will look pretty ugly with my screen zoomed in as it is, but I'm going to run this anyway and just look at a few of them. I'm going to raise my screen up a lot here. Let's just make it as big as possible and scroll up. And what we can see is this arranges the data set into a, a table where each row is one of the variables. So the way you read this is that the variable called sex is treated as a factor by the passive-aggressive butler that makes R run. The in miss and percent miss we can just ignore, and the number of distinct values. And this is one that we particularly want to pay attention to, the number of distinct values. So really we just need the variable in the class. There are a few more columns. If I scroll down, it'll start to look much uglier. There's some details for each of them. And if we like go down to this one, I think it's number 18 is an example of one that's causing problems with the display in the terminal. This is a question that is, how do you feel about your neighbors? Most people can be trusted. No one can be too careful, or it's difficult to tell where the three permitted values of that answer. And so some of the others in the survey were things like yes, no, no opinion, etc. If we translated this for your average Shropshire citizen, it might be something like yes, good British people, they might be foreign, or they're definitely foreign. Okay, so that's what that looks like. Now that's too much data for us to tackle. We've got these, if we just reprint the number of dimensions, we've got 35 columns of data, and we only have 5,000 rows. Now remember, this is a technique I mentioned that is best for very large data sets. And it's also the ideal situation is that you have a very large data set, and for all the variables, it's perfectly balanced across the levels of each variable. Of course, no data set is like that. And if you have 35 columns with just 5,000 rows, you can start to imagine the number of variable combinations that there will be. So this is one of the times when you're doing a data synthetic project that you have to make some decisions. This data set is simply not good enough. It's not big enough to be able to simulate all 35 variables. So that's one of the ways to manage the data that you have available, is to pick and choose which variables you want to simulate. Another way to do it would be to somehow reduce the number of levels by data transformation that individual variables have. We're not really going to do either of those today, but I'm just saying that as an aside. Now, they have a a function here that that I just ran, and a lot of the variables are named like this. This is the one that summarizes the data into a tabular format. And there are quite a lot of helper variables. And I find that there's almost an overwhelming amount of helper variables. This is one of the few libraries that I've used in recent years in R where I find it almost mandatory to read the user manual. It may be a bias that I have because I tend to use statistics libraries and I can infer what the tools mean from their names, but I'm just also saying that for your benefit. Okay, so what I've done here is I've gone ahead and I've cherry picked a certain number of the variables from the data set. And if you're interested to see what they are, I'll print out the tab. So all this does is it's grabbing all the rows from just a subset of the variables in the data set. And then we'll just take a look at which rows I grabbed. So pick the sex, age group, a factor with 4 levels on the education level. Now, these are codes that if we had more time, I would invite our colleagues to comment on what they mean because I don't really know what they mean, but for our purposes today, it doesn't really matter. And I've picked marital, depression factor. There's too many levels of this. I should probably drop that. The trust factor for your neighbors, trust in your family. I guess it's general societal trust, trust in your neighbors and trust in your family. And then the income. The income is being treated, even though it's a numeric value, it still gets treated with the indistinct. So that's big, and that one's okay. I guess the depression, if we treated it as numeric, it's okay as long as we don't have 22 factor levels. A numeric will be treated like a regression with just 2 parameters, a mean and a slope. Okay, so I'm happy with this. I've just reminded myself why I was happy because that 22 scared me when I looked at it. But I reminded myself why I'm happy with it. If we look at this, you can examine my code if you want. I'm not going to explain it in detail because I want to have time at the end to look at the diagnostics for this. But I just wanted to look at a weird value that I noticed. Value 603 is a -8 for income, which must be an error, I guess. And there's also one missing value. And this is another point that I wanted to mention in data synthetic projects is that if you have weird values that are real, you need to account for them in your data synthesis. So one way to account for this -8 and one way to account for the missingness variable would be to go ahead and simulate those variables as they are. And if we have a -8, what this means is that the distribution that's used for the numeric variable for the income, that would be this is in income, and it's just something that I noticed when I was looking here. That means that the distribution would have to cover at least -8, but probably it's wrong. I didn't fret over it this time like I would if this were a real data set I wanted to synthesize. But these are things to be aware of. The missingness of data. This is a thing that we tend to ignore as an annoyance when we're dealing with data sets that we analyze statistically. But we're doing simulations, especially if we're doing them on large databases. This could be a significant amount of data for some variables, and we have to figure out what to do with it. Whether we impute is the term for looking at the variables for similar data observations that we can use to extrapolate. Yeah, it could be negative income is probably for farmers. That I'll kind of laugh, kind of laugh because I don't know if you guys notice. I don't want to digress on this, but agriculture and art are actually two of the professions that you actually make less lifetime income than if you have no university degree than if you do have a university degree, which has some special implications for Harper Adams. But never mind. All right. So before we before we go on, I wanted to load up a few more tools that I found were useful, and I would always find useful for this kind of exercise. One of them is literally just a tools package for being able to do advanced things in R, dev tools. So it's a real common one. And the reason we need dev tools is because to visualize, see you later, Claire, to visualize random forests. So again, it's one of the methods that's used to impute and calculate these joint probability distributions. This GitHub-based library called repartree. So if we're going to install something from GitHub, we require DevTools on board. And so since I want to visualize one of the trees just to show you what the synthetic data look like, I want to use repartree for it. And so I've loaded it here. So this isn't required to do the actual data synthesis. The only one you need for that is the one that I loaded at the top, SynthPop. All right, so before I do the simulation, I wanted to show what this data subset looks like with respect to a tree. And I mentioned classification and regression trees. I didn't bother to put this in the talk and make a link to it, but I've said in here before that I could think easily of 10 or 50 or 100 papers that are statistical, practical, scientific papers that probably every working, especially research students, but in any scientific field would benefit from being at least aware of. And one of those at the top of my list is Brayman's random forest paper. So these classification and regression trees methods, I think this was published around 2000, 2002. I think this is one of the classic papers in all of applied statistics that most scientists should be at least aware of it. I think it's got something like 40,000 citations. That gives you an indication of how much impact it had in its time. Okay, so this function in the random forest package, the random forest function in the random forest package, is a straight up implementation of Brayman's method from way back then. And there have been some advantages I mean, not advantages, there have been some advances in statistical methodology in the random forest method since Brayman's paper, but they've actually been quite modest. They've just been tweaks. And so we're still doing this kind of modeling, which is non-parametric in nature. It's very flexible as well. It can make predictions on categories. It can make predictions on numerical variables and a combination thereof for virtually any number of variables and other parameters of interest that might be putative dependent variables, for example, and things that bother us about linear models. A lot of assumptions about distributions are not relevant. They're not a problem for the random forest method. So that's why it's such a good technique. That's why I think people should be aware of it. And it's part of the reason why I want to show you what it actually looks like, because we don't often report this in scientific papers. But you can ignore most of the way I've implemented this. I've implemented income as the dependent variable against all the other variables, and I'm just going to run the random forest and put it in a model object, 3, 2, 1. And it's going to take a second for it to run. You can see it clicking down in the console. I've done 500 trees. If you want to see what this looks like, this is the percent of variance explained by our data set. And, it turns out we don't gain very much by doing a forest as big as 500 trees, probably because we have so many variables to start with. Um, there are 5,000 variables, but that went pretty quickly, like it should on any modern computer. And there are many of these variables you can tweak. But what I'm going to do now is look at the decision tree. I'm going to visualize it, and you can already see that there's going to be a problem with this tree. I just wanted to show it to you. It's going to pop up in the plots window, and then I'll make it big. I'll pop it out and make it big. 3, 2, 1. It's going to take a second. There it is. If we zoom out, there we go. That's the problem with this tree. And this is in general a problem with classification and regression trees, is that there tend to be, with the more variables you have, the more splits you have in the tree, and the harder it is to make a sensible visualization of what the tree is like at the major nodes. But I want to show you this anyway for a particular reason, which I'll tell you in just a moment. So what I've done is I've cut down the data set quite a lot to show you a more reasonable version of the tree to make my point. So I've made a version with just 3 explanatory variables. And then I'm going to run the model again. It goes much faster because it's only doing it on 3 rather than about 10 variables. And I'm going to just print the tree again. I'm just going to zoom in again. And this still looks terrible. But what I hope you can see, if I make it just a little bit smaller, see if I can make it look a little bit better. There we go. I think it will actually look a little bit better if I do it that way. That looks a little bit better, but I know it'll be harder to see. It's actually messed up. I don't know why it's messed up. The point I was going to try to make is that we have a tree that has bifurcations in it at every node. And so up here you can see a node that's based on education for a subset of the variables that are called P, E, V, and S. Again, I don't know what the data are, but we have a bifurcation that ends in females that asks the question, yes, female, no, female, and the bifurcation goes one way or the other for each of these. And then it goes on down through many variables. My point of wanting to show you this is that when we're performing synthetic data, what happens is that the original data set that we have available has such a tree performed by way of analysis. And at each of these nodes is a weighting, a statistical weighting. And so the whole model can be represented as a set of statistical weights. And it's those statistical weights that we use to actually simulate the data. I just wanted to make that point, and so we'll stop looking at that terrible looking graph. Apologies for that. Okay. So it's so easy to do the synthetic data. Remember, now I've glossed over all of the responsibility that you would have of making sure that you're happy with all of the variable levels and the variables themselves. I've reduced the variables down. I've left in some missing variables which won't affect what we do here at all. And I've used the synthesize function, SYN. I'm just going to look in the help or the syn function and just make a point before I run it. It only takes a few seconds to run. And to make the point that, well, this is the default values for this variable. I mean, this function. And you can see, man, there are a lot of arguments with a lot of default options. And some of these are ones that most people would not use. And then some of them are very, very important to your success in this endeavor as a scientist. So I'm also glossing over that in this example, but I wanted to just draw your attention to it, that this exists and you have to take it seriously if you're going to embark on something like this. So without further ado, I'm going to go ahead and synthesize 10,000 rows starting on our original data set. Let's see how fast it goes. 3, 2, 1. That is pretty fast. And I think the reason it does this is it makes a relatively small number of trees depending on how big your data set is and how many variables you have, and then literally just does the synthesis from that. It's much, much faster than the original random forest. So we can do a summary of it. This is going to make a picture. I don't know how it's going to look with my zoom, so I may have to adjust this a little bit. Let's look at the summary. 3, 2, 1. Oh, it's just the numerical summary, of course. This is not very interesting, but what I would be looking for here is I would be looking for a comparison for some of the key variables that I may have already picked out to make sure, for example, that the sex ratio is split in the way I prefer. Now, I believe there was a slightly biased sex ratio in the original data set, and we can alter that by exploiting the some of the arguments over here that I mentioned. So fixing bias in these variables are one of the primary reasons to do data fixing with synthetic data. So I just wanted to highlight that. And we can compare, there's a whole set of graphical tools to compare your success. And I hope you're as impressed with this as I am when I show it to you. You won't be impressed with that until I make it a little bit bigger. And okay, what are we looking at here? Well, we're looking at a couple of variables at a time. The dark blue are the observed real data set, and the light blue are the synthetic data that we've just created. Remember, these are synthesized across every possible joint probability distribution for every variable. This is just a few of the variables that are highlighted, but you can see that there's incredibly close matching. We have for all of the levels, this is the education. So primary, no education, vocational, secondary, and post-secondary. Okay. So the distributions are exactly the same. For the profession, exactly the same. For the age groups, exactly the same. And it'll be like that unless there's a problem. And if there is a problem, you have to correct it because these should all have almost exactly the same height for all of the variables as the original data. Okay, so I'm going to get rid of that. And see, yeah, that's actually all that I have. It was just here. I want to show the rest of the variables. Yeah, you just cycle through by hitting enter to go through all the variables that you picked. So you can see that basically all the variables are exactly the same. I think it's funny, the distrustfulness of this is trust in the family. You trust your family. You trust general society. One can't be too careful. And then let's look at the last one. Trusting your neighbors. This might be how I feel about my neighbors. I'm not sure. Let's see. Trust your neighbors. Yes, you mostly trust your neighbors. That is pretty much how I feel. Some had no opinion. I think that's kind of mean for your neighbors. Anyway, that's all I've got. Finished a little bit early. Are there any questions or comments about this this tool? I didn't think I would have any extra time, or I would have gone a little further on the synthesis and maybe even tried something with a real data set that's probably a lot filthier than this social built-in data set to the SynthPop package. Any comments or questions? Anybody have any ideas about synthetic data for your own data? Carl?
Yeah, that's really interesting. Ed, I was just thinking about the farm business survey data that's, I mean, it takes a reasonable sample cross-section across the UK with some geographical positioning. And I was just wondering whether or not it'd be potential. Is this the sort of process you'd go through for micro simulation?
Um, yeah, I mean, if you were gonna do simulation of different types, so I've done a few types of simulation with that are analogous to synthetic data methods, and I never thought of using random forest. But the hard part for all of the for all of these methods is to have sensible data to go in and to ask a sensible data of the modeling to create the synthetic data set. Like the hardest ones, I'd have to look at the different variables that are in the farm business survey that you're talking about. But the things that uh, are hard to simulate are, for example, free answer questions, if you get opinions. But even there are even methods that are actively being developed for that use some large language models to do it. The thing about the mainstream methodologies in synthetic data with capitals for S&D is that the methods are really robust even to pretty bad data, whereas I've always had a lot of trouble unless I had real clean and balanced data before. It was always a big headache trying to do simulations. So depending on the kind of data and what the point of the exercise is, remember the greatest value for doing this is for data sets that I mean, there's a limitation that I haven't even pronounced here, which could be a limitation for the utility for a data set the like. So what you're talking about is that if if you're synthesizing a data set and you've got a small sample, but you wanted to reach a larger sample, you're not going to invent any new information through synthetic data methods. So if you're missing parts of the population, like the example I gave before with the medical data, or maybe with the farm data, maybe you're had very low uptake from Welsh farmers, for example, and it was primarily results from England. Well, you wouldn't be able to cogently argue that your data were relevant for Wales unless you tested it against a Welsh data set, which if it doesn't exist is a big problem. And it's the same kind of thing in medical data sets that's a limitation of the method. But in general, very robust. And a thing about farm data that if you have all sorts of businesses and some are rare types of businesses, I'm just making an example. It's probably a bad example, but let's say you had woman-owned organic businesses in farming, and they were underrepresented in the real data. You could probably bolster that part of your data set to make real inferences in using a method like this. So it's good for some things that I'm aware of, but there are limitations. I don't know if that answers your question.
Yeah, it made me think a lot more about how we might be able to use it. But yeah, that's great. Thanks, Ed.
I would love to use this method on the PRISM data set. I think we'd have to get permission and convince the various stakeholders that we really were doing something good and they weren't giving up anything for nothing. But I think that the carbon calculators are a prime example of the absolute deficiency of value in an individual farm just getting back their own carbon emissions every year. And even if there's some kind of higher level benchmarking that they get back, like a stoplight system or something like that, the value of having the synthetic data, for not the least of which reason to explore all those other variables that we tend to have to kick to the roadside to do the analyses we've done on it so far. I think it would be really interesting. Any other comments? Well, that's all I've got. I had so much fun doing and preparing for today's, and I do want to do some synthetic data work. I think it's more likely that I'll start doing a real synthetic data operation on the chicken data that we have access to. I see that as being less problematic than the PRISM beef emissions data that we have access to. I guess I'll just go back to the schedule real quick and just remind everybody that next week we'll be doing a power analysis and sample size. Probably be talking a lot about effect size next week because it's a new research student who has a new project, and they've just proposed, they've just learned during a meeting what effect size is. So this is new to them. So we'll be covering all the basics. So if you're interested in that, and some of you probably are if you're designing your first or second year experiments, I'll see you there. And thanks for coming. Let's stop the video.
Thanks, Ed.
Pleasure.
Thanks, Ed. See you soon.
Pleasure. See you later.